Hi guys, thanks for coming to writing your first Kotlin compiler plugin. It's going to be a pretty dense topic, so I'm just going to dive right in. If you have questions, please come ask me afterwards. I had a lot of questions as I was writing this, so I'm just going to dive in with like an intro and some like frequently asked questions. So one of the most frequently asked questions I think I get is, are these basically like annotation processors? So they kind of solve the same or similar classes of problems, like metaprogramming, but the method by which they work is quite different. So with annotation processors, your annotation processor runs a compile time, right, against some public documented API, and you emit Java source code from your annotation processor, right? And your annotation processor can run on Java code or Kotlin. Oh. Crash? Keynote. Oh, that's weird. OK. It didn't crash. It just minimized. Anyway, OK. So it works on Java and Kotlin source code, but multi-platform isn't supported, right? So the method by which capped, the Kotlin annotation processor tool, works depends on some stuff in Java C, so it doesn't work on JS or on native. So on the other hand, compiler plugins, you also run code at compile time, but you're writing code against this private API inside of the Kotlin compiler. You're emitting Java bytecode, or I'll get back to the LLVM IR bit in a second. It works not on Java source code, on Kotlin source code, because it's a feature of Kotlin C. Multi-platform is supported. So this bit about LLVM IR, you write out JVM bytecode when you want to modify stuff for Kotlin JVM. You write out LLVM IR when you want to modify stuff for Kotlin native. At some point, there may or may not be unification of these APIs. I'm not quite sure. But yeah, that's the gist of it. So why would you want to write a compiler plugin? Well, you get this incredibly powerful API. You can modify anything. You can even modify the internals of functions and classes, as you may have seen if you've used one of them. And this enables you to do some metaprogramming that you can't really do with annotation processors. And it works on every Kotlin target. So if you wanted to write a metaprogramming plugin that works on JS or native, you can't really do that with an annotation processor. You would have to write a compiler plugin. But then there's a ton of reasons not to write compiler plugins. You shouldn't just go and stop writing annotation processors and just only write compiler plugins, because they're pretty difficult to write. Annotation processors are pretty simple to write. There's a lot of great tooling out there to write annotation processors, and you have to write a ton of code to write these compiler plugins. So you don't just need to write the code that generates the bytecode. You need to write an IntelliJ plugin if you're going to create synthetic members, so that if you're writing code if your users are writing code that accesses methods that don't actually exist, IntelliJ doesn't like highlight in red, so that they can actually understand what they're doing, provide some auto completions for this metaprogramming that you're doing. You also need to write either a Gradle or Maven or whatever tool plugin, so that the user can actually configure your compiler plugin. And as I said before, it does allow you to target every platform, but at the moment you have to write different extensions for each of those targets, right? You would have to write an IR generating extension to native. You would have to write a bytecode one for JVM. We'll dive into all this a little bit deeper. So some examples of compiler plugins, if you want to look at some prior art, there's the all open plugin. I'll probably know most of these, but you annotate a class with it or a function, and it becomes open. The no-arg compiler plugin, you annotate a class with it, and a zero-argument constructor will be generated. Right? These are things you can't do with an annotation processor. You can't modify classes. You can create new classes, but compiler plugins actually allow you to modify classes and do things like adding zero-argument constructors. They even allow you to do things like with the Android extensions. If you've used these, it will add synthetic properties that don't exist really on your views, for things like this find view by ID would just be view.foo instead of view.findView by ID, r.id.foo. And also you can annotate a class with Parcelize, and it will just generate the parcelable implementation, which includes the creation of some static field, which is something you also can't do with a annotation processor. The newest one is this Kotlin serialization compiler plugin, which generates serializable implementations on The cool part is that it generates them on different platforms. So it's actually multi-platform ready. They have a LLVM IR extension for native. This was one of the big motivating factors in writing this as a compiler plugin, is that they can write, it's multi-platform ready, right? So you'll notice that all of these are first-party plugins. They all live in JetBrains' GitHub repository, right? You can go poke around in them if you want to. They live in this plugins directory. That's where the actual business logic is. So there's plugins/all-open, noarg, all those. There's also Gradle wrappers corresponding to each of them in libraries/tools/Kotlin, all-open, noarg, etc. There's also Maven wrappers for most of them. Obviously not for the Android ones, but for most of the other ones, there's a Maven wrapper for them as well. So you can go look at these. But you can build one outside of the JetBrains first-party like repository ecosystem. You can build a third-party one and publish it. So today I'm kind of going to walk you through publishing one using, we're going to publish it and allow consuming it from Gradle. So we're going to write a Gradle wrapper for our compiler plugin. And it will be publishable. You could publish it as an artifact to Maven Central or JCenter or anything like that. So we're going to look at the architecture really quickly. I'll put this slide up multiple times throughout the talk because the names are really easy to forget, and there are a lot of them. So this first part up here, you can use the laser, cool. This first part up here is, this is going to be, we're going to create two separate modules, right? So up here is just a Gradle wrapper. This is kind of just like an entry point from Gradle. Down here is really the big logic of it. This is the Kotlin plugin. So we're going to create two modules within this project that we're going to write. And they're going to be a Gradle module and a Kotlin module is the nomenclature I will use. The Gradle module being just a wrapper around this Kotlin module. So I'll dive in and explain what each of these classes do one by one. So the plugin class this is just part of the Gradle API, and it's not really related to Kotlin in any way. Any Gradle plugin you write uses the plugin API, and it just provides you an entry point from your build.gradle script. And it allows you to configure your plugin via extensions. So if you've written, for example, an Android app and you've seen that Android curly brace, and inside of there you can define things like your min SDK version, that's defined as a Gradle extension. So this is where you define user configuration, essentially. Then your sub-plugin will get called. So the sub-plugin is kind of the interface between this Gradle API and the Kotlin command line processor, which lives underneath it, of course. What it basically does is allows you to read in these extensions that were defined in your plugin, and you write out sub-plugin options, which are essentially key value pairs that are passed to the command line processor. You also will define something called a plugin ID. It's an internal key that really namespaces your compiler plugin options so that they don't collide with other plugins. You also will define a set of Maven coordinates, essentially, to go download this module, right? This will be published as a separate module. This Kotlin layer will be published as a separate Maven Gradle module, and you'll provide the coordinates for it to be downloaded at compile time. So that's the high-level architecture, right? We're going to dive into this is the actual like Kotlin. We're in like the Kotlin command line processor level now. Like we're not in the calling it from Gradle level now. So this is where you would read in, if you've ever called Kotlin C directly from the command line, or if you've called it from IDEA, IDEA essentially calls through to this, and it passes as X plugin args. So in the command line processor, you read those X plugin args and parse them. So your sub-plugin, actually, when you create those sub-plugin options, they get passed through this pipeline as well, and they're namespaced according to the plugin ID. So you write out something called a compiler configuration key from here, which is kind of similar to these plugin args. There's some differences. You can have multiple X plugin arguments, for example. You usually will have one compiler configuration key, and they're typed. So really, this is kind of just an opportunity for you to take these key value pairs and like map them to real types, like richer types. And then those get passed to your component registrar. So your component registrar really just reads those keys, and it registers extensions. So I know this is a lot of kind of ceremony, but like we've finally gotten to the extensions, and there you can register multiple ones from your component registrar, and these are really like the meat of your plugin. This is where you generate code, right? So there's a lot of types of extensions. You can extend from a lot of types of them. There's expression code gen extension that hooks into the creation of bytecode from an expression, and you can modify that bytecode. There's class builder interceptor extension, which does the same thing for classes and functions. There's Other ones, there's storage component container contributor. I don't quite know what it does, but I know Android Extensions uses it. There's IR generation extension, which is a cool new one. This lets you generate IR instead of bytecode. The other ones were all written to generate bytecode. This one generates IR. So from all those other ones, you would be writing bytecode. This one allows you to write IR. If you write one of each, for example, you could generate both, and that's how you have a multi-platform ready compiler plugin. So given this architecture, right, we can write our own compiler plugin now. So let's kind of dive in and come up with a use case that can't be solved by annotation processing so that we can actually write a plugin that makes sense. So we're going to write one that traces method calls. There's stuff out there that does this, but one way to solve it is via a compiler plugin. So if you're going to annotate, you can annotate a method with a debug log annotation, and its method body will actually be modified to include logging. So you can't do this as an annotation processor, right? With an annotation processor, you can only generate new code. You can't modify the user's code. But some people I'm sure will say, like, there is prior art around this. Jay Korten wrote Hugo. Hugo is a library that does exactly this. There's Firebase performance monitoring, which has an add trace annotation that also does this, but logs it to Firebase. So these solve this problem via AspectJ bytecode weaving, and they use the Android Gradle transform API as like a hook into these functions that you've annotated. So similarly, we're going to be modifying bytecode. We're going to do it via the Kotlin compiler. I believe that these libraries only work on Java and not on Kotlin. Ours will work on Kotlin, of course. So we're going to build this using a compiler plugin. So basically, the goal is to get from this. Let's say this is going to be the sample I'll use throughout my code. It's a prime number calculator, right? You pass in that you want the nth prime number, it returns that to you. So really, I have all this ceremony, and all I actually care about is writing this, right? Writing this function that takes from a lazy sequence of prime numbers, takes the nth element. But I have to write all this code around, like logging what the name of that method is, and the parameter that I passed in, and how long it took to run. So really what I want to write is this. I want to write an annotation on my actual code without the ceremony, and all that ceremony is kind of just done for me, right? So there are ways to do this with like inline functions and execute around method, which Hwen talked about in her talk today, but you can't do things like get that function name, right? You wouldn't be able to do that with an inline function. You can't get those parameters. I want them dynamically loaded. Let's say I add a second one to this function. I don't want to have to go in and modify some logging. I want it to just happen, right? I want them to be comma separated. You can do this kind of stuff with an annotation processor. So let's dive in and build one. Again, here's the architecture of this. We're going to start at the top. We're going to go top down so that we can trace through how this code is actually called as we do it. So first, we're going to write the build.gradle for our Gradle module, that part that's in the Gradle braces, right? So here's the build.gradle. The only important parts are first this Java Gradle plugin. So this allows you to write Gradle plugins. It's a plugin that lets you write Gradle plugins. It also gives you access to this syntax where you define two strings. You define the ID of your plugin. So when you define this ID, basically you're saying that users will do this. They'll do apply plugin, this ID, when they want to use your plugin. And when they do that, this is going to be called, this implementation class, which we're going to define. So you do all this. The nice part about using this plugin is you don't have to do what you may have done in the past if you've ever written a Gradle plugin, which is create a source main resources meta-inf file. Similarly, you would have to create one of those for your sub-plugin, but we're going to use autoservice to avoid doing that right down here. Basically, the goal of using these libraries is I only want to write build.gradles and Kotlin source files. I don't want to write weird asset files and resource directories and things like that, and these libraries will enable us to do that. The only other real thing you need here that's important is this Kotlin Gradle plugin API dependency, and that gives you access to things like sub-plugin. So this was a lot of setup, right? Now we can start to write some code. So let's write the actual plugin class. Let's write what gets called when you call apply plugin. So we're going to extend the Gradle project class. We're just going to define an extension. So by doing this, we're saying the user can write debug log, open up curly braces, and essentially define these properties. They can modify them. So these properties, we're going to create this class on our own. We're going to say the user can disable it at runtime, at build time rather. In their build.gradle, they can say enabled false. And they're going to define a list of annotation fully qualified class names that mean please debug log this. So that's our entire plugin. We can just move on to our sub-plugin now. So our sub-plugin, so first we're going to extend Kotlin Gradle sub-plugin, which is the class that enables us to be a sub-plugin, be a Gradle Kotlin plugin. And remember to register it with auto-service, otherwise it won't run. So remember to do that. And when you do this, you're going to have to override a few methods. So we'll go through them first super quick. Is applicable is really easy. You just check if the project has your plugin. So we're going to reference that class from earlier, check if that plugin is there. If it's there, we can apply this plugin. So the next function is the compiler plugin ID. This is going to be just an internal string. The user would see this if they called from Kotlin C directly, but this allows you to namespace the arguments that are going to be returned from this apply function later, this list of sub-plugin options. Really, it's just important to be consistent with this. So we're going to use it again in the command line processor later. So I've chosen debug log. Then we're going to override get plugin artifact. This is going to be where I mentioned before the Maven coordinates for your Kotlin plugin, the other layer that we're going to write next. So for example, I'll have to bump this version in tandem with any updates I push out, because this is where this plugin is going to look for the actual command line processor business logic. And then you can override the apply function, which will really just take your extension and write out a list of sub-plugin options. So this is kind of the meat of what the sub-plugin does. So we're going to, I'll push all that other stuff off the screen because it's a few lines of code. So I'll run through them one by one. First, you just grab the extension that you defined before off of your project. And if the user did not define one, you'll grab a default one. You'll create a default one. So we're going to do a quick sanity check and see if the extension is enabled. If it is, make sure that they actually defined some annotations to use as debug log. If they didn't, we'll fail their build because they should just turn our plugin off or define some annotations, right? So now what we can do is we can actually take those options and create some sub-plugin options off of them. So we're going to take all of their annotations and we're going to map them to sub-plugin options, which are essentially, as I said before, key value pairs. So those annotations are all going to go into this debug log annotation option. You can have multiples, so I'll map them to a list of those, and I'll also create one called enabled for my whether or not it's enabled, essentially. Just turn it into a string, true or false, and we're going to return a concatenation of all of those. And again, it's okay if these names collide because the compiler plugin ID we defined earlier namespaces them later on in the pipeline. So we've written that. That's it. We're out of like the Gradle land of this all. We're now in the command line processor, which is totally build tool agnostic. This is where your Kotlin C plugin args are parsed. And again, Gradle just uses the same pipeline. So we're going to define a new a new module in our project. So this one's a lot simpler in terms of dependencies. It'll have a lot more logic in it. The first thing we need auto service again so that we can register a few more classes that are going to be used as services. We also need a dependency on this Kotlin compiler embeddable. It only needs to be compile only because we just want to be able to extend some classes that are defined in the Kotlin compiler. We don't need them at runtime just because the Kotlin compiler will provide them. It'll already be there in the environment. So we'll depend on that, and that will give us access to the classes we need to write our command line processor. So we're going to extend off the command line processor, which is part of that embeddable compiler package. We're going to remember to register with auto service, and we're going to override these classes. So override these functions, sorry. So the first function we override, we give the same string that we gave before in our sub plugin. This allows it to know which namespace to take all these plugin args off of. Then we're going to override plugin options. This is kind of the same options we gave before, but we have a richer type now called a CLI option. So you see enabled there, you see debug log annotation there, and there's some descriptors there about what type of values can go into it, and kind of a long description of it. In addition, for debug log annotation, I've defined that it's required because you have to give me at least one, and we'll allow multiple occurrences because you can have two or more, right? You could have multiple things that you want to use as debug log annotations. And then process option is where you're going to take these plugin options and you're going to write out compiler configuration keys for them. So what we're going to do is we're going to wind on the option name, and we're just going to create a case for each of these plugin options, right? You can see that this matches up to the plugin option up there. So we're going to put a compiler configuration key. I've defined this elsewhere. This is a key of type Boolean. Of that value, we're going to parse that string, true or false, to a Boolean, right? And for debug log annotation, it's not configuration.put, we're gonna use .append list because if they passed in 2 or more, we don't want to clobber their previous ones. Configuration will basically just manage internally creating a list of those and appending them. And if we hit any other one, we'll just error out because they should have defined it. We should have defined it in our CLI options, basically, in our plugin options up here, right? No other option should ever come through to us. So that's our command line processor. We've essentially taken these key value pairs and written out richer type compiler configuration keys. And now we're in the component registrar. I know it's a lot of ceremony, but we're almost to the part where we generate code. So now we're going to extend off of component registrar. We're going to define this with auto service again. We're going to register it, and there's just one function you override. And in here, you can read keys off of your configuration. You can see we kind of use this map-like syntax with our compiler configuration keys to read off of it. So they're all nullable, so I'm checking if this configuration is false. If it's explicitly defined as false, we'll return. If it's true or if it were implicitly not there, we'll default to true, right? So we'll fall through, and this is where we actually start registering extensions. So simple compiler plugins like noarg will have one thing registered here. Android extensions has several. Depending on what you want to do, you will have something in between. So for example, this is where Kotlin serialization would register a JVM bytecode extension and an LLVM IR generating extension. So I'm registering a class builder interceptor extension for this because I want to hook into every function that's being built on a class, see if its annotation is there, this debug log annotation is there, and if it is, we're going to intercept the building of that function. So we have to pass in the project to this register method. We also have to create an instance of this interceptor, which I'm going to define next. So this is the pipeline, right? We're pretty much out of the actual pipeline. We're going to write this debug log class generation interceptor now. I know there's very long names involved here. So this is one of the extensions of this pipeline. And we're going to actually generate some code, right? We're going to generate some JVM bytecode in our case. So this class is extending class builder interceptor extension, which has one function. That function takes a few arguments. I really only care about this intercepted factory because this is what actually builds classes, and I want to intercept that logic, and I want to do something else. I want to hook on some other stuff. So we're going to use Kotlin interface delegation to use almost the same logic in this intercepted factory, but also I want to override the function called new class builder, and I want to hook in my own logic. So I'm going to create another new class called debug log class builder, and it delegates through to the default implementation from this intercepted factory, which is right here. So we're going to go build that debug log class builder now. So it's a delegating class builder, which means that you don't have to override the many methods it has. But we're going to override one called new method that has a bunch of arguments and returns a method visitor. So we're getting like very Gang of Four design patterns here, but it's okay. You don't really have to like know visitors and delegates and all those things, kind of. You don't really have to know how the visitor works under the hood. You also don't need to know all these args. You really only need to know the origin. The JVM declaration origin has, for me, all the info I needed to build this. So the method visitor, by default, you get a method visitor out of the super implementation of this, right? Which was from that delegate that we passed through. So I want that default implementation because that's the user's actual logic that they built. I'm also going to take this JVM declaration origin and I'm going to grab its function descriptor. I cast it because I'm pretty sure it's always a function descriptor. If it's not, I'm not sure what scenario that hits, but I'll say return out the original implementation. Then I'm going to check if any of the annotations on that descriptor match up with my annotations. If they don't, also return the original. So now we've fallen through, right? And that means that we have this function that has an annotation that matches up with the list of annotations the user gave us. So we're going to kind of inject some logic in here. So we're going to create a new method visitor. And this is like a very scary word that is opcodes ASM5. It just means like it's part of this library that JetBrains uses internally called Object Web ASM that has nothing to do with ASM or Web ASM or anything like that. It's just a library for modifying bytecode. And we have to specify a version. And we're going to pass in our original method visitor. So this is kind of where we're going to start generating JVM bytecode. So this is part of the Object Web ASM API. You can look it up, but its contract tells us that there's a function called visit code that has to be visited when you enter a method body. So if we want to do something on method entry, we can hook into this method, and we call it super implementation. And we're going to also create something called an instruction adapter in there, which allows us to create JVM bytecode on this, basically on this part of the code that we're visiting. So there's a DSL for creating bytecode included with the instruction adapter. So in there, I'm going to do what I want to do on method entry. To do what you want to do on method exit, you have to kind of understand JVM bytecode instructions. So the JVM will put the value you want to return on the stack and then call one of these opcodes, return or a return for returning an object, or I return. There's also LD for long, double, return, all those things. I didn't want to include them all on the slide, but basically what we want to do is intercept calls to that opcode, because now our return value is on the JVM's stack, and we want to intercept it there, and now we can do stuff on method exit with the return value. And also, we want to pass through to the actual implementation, right? We don't want to clobber the user's implementation. So we have all these hooks in to do finally what we want to do, right, on method entry and exit. So now we have to figure out like what we're going to do. So we're going to write some bytecode, right? And what does that really mean? We're going to write it using the Object Web ASM API, which provides us this DSL. It's like not assembly, it's not WASM, it's not any of that stuff. It's just modifying JVM bytecode. I'm going to do like a quick like crash course of JVM bytecode, because I didn't understand it when I started this talk, and now I kind of probably don't understand it also, but enough to talk about it. So it's a stack machine. You get an operand stack, and that's where all your methods push and pop onto. It's like a stack like you may know from programming. And there's also a local variable array that you can kind of read into via indices, and you can store things in it and take things out. And I'm sure I will get many things wrong, and I apologize in advance to anyone that works on this. So I want to show, this is a simple like sample, right? You write Kotlin code that has these two methods that return an integer, you sum them up and you print it. This is the bytecode that comes out of it, right? So it's very scary. I know like when I saw like invoke virtual, at first my eyes like glazed over, but I want to walk through it like line by line and show you what happens on the stack when you do this. So we're going to go through like line by line in this bytecode. So first there's this invoke static function that on runner KT is my class called v1. This means that it takes no arguments, it returns an integer. So by doing that, you're putting an integer on the operand stack. Then we're going to call v2, which, as you can imagine, does the same thing. It just puts the return value of v2 on the stack. Then we're going to call iadd, which is an opcode in bytecode that takes two values off the stack, and it returns the result of that addition and puts it on the stack. So now our stack has the value of these two things added together. So now we're going to store it. iStore means integer store, as iadd meant integer add, by the way. You have to use ladd for long, lstore for long storing. So we're going to store an integer into our local variable array, which I mentioned before is kind of like an indexed array at position 1. So it gets taken off the stack and put into our array. So now we're going to call getStatic on the class. This is Java Lang system. I truncated it because it would go way off the slide. So we're going to get the field called out on system, which is a print stream. So you can kind of see where this is going. We put our print stream onto the stack. That's the standard out print stream, right, when you call system.out.println. So then we're going to create a new string builder. So by creating a string builder, we put it on the stack. Then we're going to call dupe, which puts another reference to that string builder on our stack. And the reason we need to do that is because when you new things up in bytecode, you don't actually create, like, invoke its constructor. You have to explicitly invoke its constructor via invoke special. And init is the name of a constructor in bytecode, and this v means return void, and this means it takes no arguments. So we're going to call its constructor, and that takes one reference to it off the stack, but now it's initialized, and we still have another reference to it, right? Now we're going to call load constant. I hope everyone's kind of with me here still. This loads a constant onto the stack, right? So we're going to load, for example, sum of values was. That's like a constant at compile time. Then we're going to call invoke virtual. This is very wrong, but for the purposes of this, like virtual means not static. It means like a member function. Just think of it that way. So like you're invoking a function on your string builder called append. It takes one string, this L at the beginning, and semicolon at the end is just how objects are represented in bytecode. So it means a string, and it returns a string builder. That's what that means at the end. So what this does is it takes your string builder and your string as receiver and first argument of this function. It will take them off the stack. It will return back a string builder, right? That goes onto your stack now. So now you have a string builder that internally has sum of values was appended to it. And then the next thing you're going to do is call iload1. And if you remember before, we called istore1. We're going to get back the value we stored before. We're going to get that value back, and now we're going to append it into our string builder. We're not going to use the string version. We're going to use the integer version of this function, and it's going to take those two values off the stack, similar to before, return the string builder, which is the same string builder from before, but now it has our sum appended into the string builder, right? The next thing we're going to do is invoke toString on that string builder, which just takes it off the stack and replaces it with the built string version of it. Then we're going to call printstream.println, which takes, if you remember this, which we loaded way earlier onto the stack, we're going to take that as the receiver and take a string as our argument and return void. So that's system.out.println with a bunch of stuff in the middle. So you loaded up that system.out first, and so you loaded up system.out first, and now you're taking it off the stack to print to it. So that's kind of how bytecode works. I wanted to show you that so we can actually write some. Okay, I have time to write some. That's good. So remember, we wanted to do this, right? We wanted to avoid all this ceremony and just like add debug log as an annotation and just do all this stuff. So since we have these hooks for method entry and method exit, we can do this on method entry and we can do this on method exit now. So in bytecode. So it's going to be complicated. So let's go back to that. And the first thing we're going to do is look at the visit code method. We're going to specifically override this method entry code. So we're going to start writing. This is a DSL that looks kind of like the bytecode we just saw, right? It's just not caps lock. It's not yelling at you. It's just get static. And then you pass arguments that are kind of what it concatenates together into the bytecode representation of it. So, excuse me. So first, you'll pass the receiver, well, the class that it's operating on, rather, for static. So it's a static function on system called out, and it returns println, right? Similar to before. Now we're all bytecode experts, sort of, and we know what's going on here. So we put a print stream on the bottom of our stack. That's our standard out. The next thing we're going to do is create a new string builder. And the next thing we're going to do, of course, is duplicate it because we need to call its constructor, right? So we're going to invoke special. Again, similar to the bytecode, this is just a DSL that invokes special. So it's going to take our, we're going to call init, and it's going to take, specifically we want to call the 0 argument constructor, and constructors are always void. So it's going to take that off the stack to call its constructor. Then we're going to, so this calls LDC, which is load constant, and we can pass a constant to it. Now that function is that JVM declaration origin function from before, if you remember, that function descriptor object. It has the function name on it. What's really cool about this is we can load like arrow prime for my prime number generator function onto the stack constant at compile time, right? Like when you call append in the bytecode, it's going to be loading a constant string because we know this at compile time. So we're going to load prime onto the stack. Well, this arrow prime syntax that I wanted. Now we're going to call invoke virtual, and we're going to append this string into the string builder. That should really say Java lang string, right? Because we're appending a string in, but it will, the point gets across. So we're going to invoke this function that will take a object or a string, return a string builder. So it will take our receiver and our first argument, and it will take them off the stack. It will return back the result is string builder, which is, as you know, string builder returns this when you call append. So same string builder goes back on the stack. Then we are going to, this is a big block, and I'll go through it one at a time. But so function doesn't just have name on it. It also has things like the actual parameters that are on it. Obviously, at compile time, you don't know the values going into that, but you know things like the name of those parameters and their order. So we're going to do an indexed for loop over them all. And line by line, what we'll do is we're going to LDC load constant that parameter's name equals. It's going to put, in this case, the prime function, remember, that I wrote before, has one parameter called n, which is an integer. Load that onto the stack, n equals. Then you're going to invoke virtual to take that string, append it into the string builder, and JLSB Java lang string builder is going to be returned back, right? So this next opcode, it's going to call a load under the hood, which is, it loads an object. In this case, n is an integer, but so you would really want to call iload, but you really, in your JVM bytecode, you have to special case everything for every primitive. I simplified it and assumed everything would load fine as an object. It really wouldn't because it's an integer, so you would have to call iload and special case this. So we're going to load the value of n, but the value of n, like, why is this the value of n? So when you first enter a function, what's in your local variable array, which is what a load loads from, is every parameter passed to the function. So your first parameter is at 1. I believe your receiver is at 0 to your function. So 1, by loading 1, we can load this first parameter passed to this function. So we're going to load up the value of n. So you remember before we loaded n equals at constant, the reason this is loading somewhat differently, instead of LDC, we're not loading a constant. We're loading an actual value from the code that we wrote. So this is dynamically loaded up and appended into our string builder. Again, I should use I here instead of L Java lang object because it's an integer. You would have to special case that and detect that it's an integer. But to simplify this, we'll just assume that it works. So you're going to append that integer that I loaded up, which is the value of n, into our string builder. So now our string builder says, it says arrow prime parentheses n equals and the actual value of n, right? And we did that all in bytecode. So that's what we wanted. I could also show you how to append an ending parentheses, but you know it'll look exactly the same as this. So I'm going to toString it, which takes it and turns it into a string. And then I'm going to print stream, right? Remember, we loaded this up at the very beginning, and now we're going to use it at the end. We're going to print line into this print stream and give it a string, and it returns nothing. So we just system that out, that print lined all this dynamically loaded stuff, prime n equals the actual value of n. So now we did some debug logging using just bytecode, right? What we also wanted to do is we wanted to log how long a method took to run. So we actually need to do that at the start of the method. So we need to call system current time millis statically, right, which returns j is long. I don't know why L is not long. I guess because j is after I, and L is a long is a longer int. So j is long. So system current time millis is a long. It returns a long and puts that long on the stack, right? Now, I think you can just store randomly into the local variable array. So I just chose an index, and I will take it out later. I'm not sure if this is very wrong to do, but it works. I don't know how you avoid collisions. To be quite honest, I need to talk to someone about it from JetBrains probably, who will yell at me for this. But I'm just going to store it into an index, which takes it off the stack. So now that index on my stack has this system current time millis at the start. Sorry, this index in my array, not in my stack, has this system current time millis at the start of the method, right? So now this is pretty much done. We've done like benchmarking code, sort of. So if you remember, this instruction adapter was inside of visit code. So that's written now. Anything else that the user runs will run now. Like in this function body will now run. So the next thing we need to focus on is what happens on method exit, which is when this block will get hit, right? Whenever an opcode for some return happens, that means that the function's about to return. So now we're going to write the code that hooks in on method exit, the bytecode that's generated on method exit. So first thing we do, similarly, we're going to load up a print stream because at the end, we're going to system out print line it. So we're going to make a string builder. You all know this. We're going to dupe it. We're going to call its constructor, right? I can kind of like speed through this now. We're going to load up another constant that says function, which again is prime, in this case for my code sample, ran in however many milliseconds. Now we need to calculate those milliseconds. So we're going to append this into the string builder. So the string builder so far says prime ran in. Now we're going to calculate the new current time millis at this time, put that on the stack. That's the current timestamp. Now we're going to load up from our local variable array. I guess I'm hoping someone did not collide with that index, right? So I'm going to load that up. It worked when I tested it. Worked on my machine. So works everywhere. So now, now my stack has the start timestamp on the top. It has the current timestamp underneath it, right? So what I can do is I can call sub. This is special syntax that's going to call L sub. This long type is like Java lang types type for long, right? It's like long.class. And under the hood, object web ASM knows to call L sub. And if I passed integer, we call I sub. What that does is takes two things off the top of the stack, subtracts them. Now I have the amount of time that this function took to run. And I'm going to append that into my string builder. And now my string builder says prime ran in however many milliseconds it ran in. And I'm going to append milliseconds to it just to make it look nice, right? And now I have this string builder. We all know what happens next. I toString it. Now it becomes a string, and I'm going to print it out. So now this is our benchmark printing code, right? That's going to print out the benchmark at the end of the function right before it exits. So that is the method visitor, and I can show you a demo because it works. Amazingly. Hope it works right now. All right. Okay. So can everyone see this, sort of? My colors look super saturated up here. So I have this main function, right, and it calls, it calculates the 20,000th prime number. The reason I'm returning this box, essentially, is because I did not want to deal with special casing integers. So all my code kind of deals with objects, my bytecode. You would have to write bytecode again. You would have to write bytecode generation code. Again, that's special cases for every primitive type. This is just a lazy sequence of every prime number, so it'll just take the nth prime number. But that's not the cool part, right? So if you run it, I want to run it first without debug log, just to show you that it really does nothing. So I'm going to run it. You can see down here, it's built. It's actually going to run now. And it ran, and it took 7 seconds to do it. It took 7 seconds to calculate the 20,000th prime number. Now, if I annotate, where am I? At debug log, right? And I run it again. Now, I didn't change anything else, but as soon as I enter the method, that trace is going to be printed with the actual value of the prime number. And it took 7 seconds to run, 6 seconds this time, 6.7. And it printed out the value that was in there. It printed out the toString of this data class, right? So it works. So yeah, thank you. So yeah, so I'm pretty much out of time, I believe. It ends at 4 and it's 3:56. So perfect timing, because that's pretty much all I have. There's resources here about what to look into if you want to build your own. You can look at the source for plugins. You can look at noarg is really simple. It's good to look at. Android extensions is super complicated, but it's like you can see use cases of things like class builder, interceptor extension. Kotlin serialization I haven't looked into so much just because it's so new, but it seems documented very well, and it's cool if it's the only source right now of how you can look at IR generation extension, which is the class that generates IR. So if you want to do Kotlin native, if you want to write a multi-platform plugin, this is what you look at. And then these are all of the corresponding, as I said before, Gradle wrappers. So you remember from our architecture before, all that stuff above the Kotlin braces, the Gradle braces stuff up there, that's all in here, along with Maven stuff. They're all pretty similar, so I kind of just look at the simple ones, because you're going to write a plugin that defines some options. You're going to write a sub-plugin that reads them and writes them out to key value pairs. So I kind of just look at noarg and all open, because they each have like one option that's super easy to read. Yeah, these are resources. So look at it. If you have any questions, come ask me. If you hate my bytecode, come tell me. Thanks. Yeah.